Good evening, student. So in the last class, we have discussed up to this particular slide. So we discuss selection operator. So we are discussing selection operator, and we have discussed mainly the tournament selection. Okay. So so far, whatever we have discussed that. So what is GA? We have discussed. Then we have given the simple genetic algorithm, the flow chart I have given. And the flow chart, if you go through the flow chart again, what we are doing, we are creating some initial solution. I have not discussed yet how to create initial solution, but today I will discuss again. When I will discuss, or when I will solve a problem, then I will discuss how to create the initial solution. And after that, you are calculating fitness function that I have discussed, how to calculate fitness value of all the solution in the population. So that I have discussed. And then finally, if you are not getting optimal solution, then what you have to do, you have to go through these three genetic operators. Okay, that is selection, crossover, and mutation. So now we are discussing the selection operator, then we'll discuss crossover and mutation, and this population will go through these three operators, and then basically this iteration will continue, and as long as the termination criteria are not satisfied. Okay, so in the last class we have discussed up to this particular slide, and this is related to tournament selection. Okay, so what you are doing here, so you are selecting a few individual, and then you are asking them to go for tournament. Okay, so as I said that suppose there are 6 solutions here. So if tournament size is 2, that means at a time you are picking up 2 solutions, and then you are asking them to go for a tournament, and one will be the winner, and the winner will go to the next generation. Okay, so if the tournament size is 2, how many tournaments you can play? Because your total population is 6, so you can play 3 tournaments. Okay, so 3 tournaments mean you can select 3 winners. But what is the total population? Total population is 6. Okay, so I need 6 solution. So to get another 3 solution, what I am doing, I am playing the tournament for another round. Okay, so that is for the second round. In the second round also there will be 3 winners. So first round 3 winners, second round 3 winners, so altogether you are getting 6 winners. Okay, so now in this case what we have done, we have taken tournament size of 2. Now if you are taking tournament size of 3, suppose this is 3, I am taking tournament size of tournament size of 3. That means then every round how many tournaments you can play? So you can play tournaments of 2, because you are selecting 3 your individuals for the tournament, total 6 population, so you can play 2 tournaments. So you are randomly picking up 3 individuals, and they will go for tournament, and one will be the winner, and then next 3 will be will be taken, and they will go for tournament, one will be winner. That means every round how many solution you are, how many winners you are getting? So you are getting 2 winners. So in order to get 6 solution, okay, so total population is was 6. So in order to get 6 solution, what you have to do, you have to play the tournament 3 times. Every time you are getting 2 winners, so 3 times you have to play, and then you will get the 6 winners. Okay, now if you look at whether your tournament size of 2 and 3, okay, so what is the difference between these two? Okay, so if you increase the tournament size, so as I said that minimum tournament size is 2. Okay, so you have to select, because one person cannot play this tournament, so you have to have 2 person or 2 solution for the tournament. Minimum is 2, and what is the maximum value? Now if I say that 2 to 3, then what will happen? The best individual, he will play the tournament 3 times, and every time he will be the winner. That means the best individual will have 3 copies if you increase your tournament size from 2 to 3. In case of 2, the best individual will have 2 copies. Okay, because he played the tournament twice. If it is 3, tournament size of 3, then he is playing the tournament in the third time also, and he will win. So what will happen if you increase the tournament size 2 to 3 or 4 or 5? Then what will happen, the number of copies of the base individual will increase. Okay, and that is not a healthy situation. We don't want that. Actually, we want the diversity in the population, and therefore generally we do not use higher order tournament size. Okay, so 2 is fine, 3 is also okay, but more than 3, then what will happen, the pressure will increase. Then that is called in that case what will happen, the better individual will have more copies. Okay, there will be no diversity in the population, and that is actually, you may get some pre-measured your solution. Okay, so you may not get the exact optimal solution of the problem. So therefore we generally avoid that one. So tournament size of 2 is fine, 3 is also you can take, so but not the higher order tournament size. Okay, so we'll avoid that one anyway. So I will discuss this thing when we'll discuss the other operators, crossover and mutation, mainly crossover operator. So you can see what could be the difference you may achieve if you increase the tournament size. I hope this is clear to you. So this is your related to your tournament selection. Okay, so now let us go to the next selection operator. So there is another selection operator, we call it roulette wheel. Okay, I will discuss an roulette wheel and proportionate selection. So these two are little bit similar. So so I will discuss it together. So let us go to the roulette wheel. Okay, so what we are doing here, okay, so I think you have played roulette wheel. I'm not sure actually. So if you have played roulette wheel, then you can see that roulette wheel actually okay, let me show the roulette wheel, and then I will explain this one. But before that, suppose we have 6 solution. Okay, so 6 solution we have, we call it chromosome. Okay, so 6 chromosome we have, and so uh, we have we have 6 solution here. So here what we are doing, so the parents are selected according to their fitness value. Okay, now the better chromosome will have more chances to be selected. So now what we are doing, basically we are selecting the chromosome, we are selecting the multiple copies of this parents solution, multiple copies of this solution for the next generation. Okay, so that basically we are doing. So these parents, basically suppose there are 6 chromosome we have, and these are the fitness value of this chromosome. Okay, so I'm putting, and here what is happening, please don't confuse this thing, that as I said that you can use the fitness value. Suppose if it is a maximization problem, maximization of fx, so basically if fx is more, then the solution is better. But if it is a the minimization problem, then what will happen, the fx value is less, means the solution is better. So what we can do, basically, so I can write my algorithm something like that, or otherwise if you are a little bit confused initially, so what I can do, that I can convert my minimization problem to maximization one. In that case I can use the same rule, that means the maximum value of f means the better the solution. Okay, so how I'm converting, so yesterday I said that I can convert that this is 1 by 1 plus fx. Okay, so I can use this conversion, and to convert a minimization problem to maximization problem. So this is your maximization problem. Now in this case, so what is the fitness value? So fitness value is telling if the fitness value is more than this, that means solution is better. Okay, so the first solution, the fitness value is 50, so this is the base solution of this particular population. Okay, then second solution is 6, that means that is the worst solution, and other solutions are 36, 30, yeah, 36, 28, so they are between your base solution, base individual and the worst individual. Okay, so this is now what roulette wheel or proportionate selection is doing. So it is actually calculating base it is based on their fitness value. That means the fitness value is 50, that means he should have the higher probability to be selected. Okay, so and fitness value of 6, that means that is the worst solution, and that actually should not be yeah, the probability is very low, and that it will be selected for the next generation. So how to do that? What I'm doing, I'm just creating a roulette wheel based on their fitness. Okay, so roulette wheel, suppose if I say the total perimeter is twice by r, okay, and this is 100%, this is perimeter is twice by r. Okay, so this is the perimeter of the roulette wheel. So what I'm doing basically, so I am dividing this perimeter based on their fitness, your fitness value. So now total is 100%. Okay, total is 100, and then this is 50%, means so total fitness is 186, so 150 divided by 186, so I should get 26.88. that means the first solution will cover an area, it means the perimeter equal to 26.88. Similarly, the for 6 it should be 3.47, then 36 the 20.81, 30 17.31, 36 again 20.81, and 28 it is 16.81. So this is the proportion in the roulette wheel basically, so based on their fitness. Okay, now basically, so I have drawn the roulette wheel here. You just see the solution 1, that is the base solution, and it is occupying 20, yeah, it is occupying, I think there are some problems, so it should be your 26.88 percentage. Okay, so similarly this is second solution, this should be 6 percentage. Okay, and then that third solution will be 20%, something like that, so 20, yeah, so it is around 21%. Okay, then yeah, fourth solution is around 18%, and then this is again 21%, and this is 16%. I think this is, yeah, this is correct. Okay, so now what you're doing here, so you are distributing the roulette wheel based on the fitness value. Okay, so based on the fitness value you are distributing this roulette wheel. Now I think there is a suppose cursor here, and what I will do basically, so I will basically, if I apply, so if I apply the roulette wheel concept, so what I will do, that I will play this roulette wheel. So how many solution I have to select? I have to select 6 solutions. So that means what I will do, I will rotate this roulette wheel for 6 times. Suppose first time you are rotating, you are getting 1 solution, suppose cursor. So probability is that now, so 6 is suppose the solution 1 is occupying 26.88%, the probability is that, so he will be that particular solution will be selected. Okay, but the solution 2, it's a 6 is basically 6, and this is your 2.47%. so there is a probability, the probability of selection of that particular solution is very less. So what I will do, so I will play the roulette wheel and then 6 times, and I will get 6 solutions. So in that case, the probability of selection of the worst solution is basically almost your 0. It may be selected by chance, but the probability is very less. Okay, so you are getting 6, but the solution having higher your fitness value, so probability of selection is very high. So based on that, you are getting 6 solution. Okay, so this is your roulette wheel, your selection. And then what I can do, I can also use the proportionate selection. So proportionate selection is basically, so I am just calculating the expected count. I am calculating expected count based on the percentage it is occupying in the roulette wheel. Okay, so it is basically the total solution is 6. So now the 6, your 26.88% of 6 is, it is coming 1.61. Similarly, the 3.47% of 6 is coming 0.19. Then 20.81% of your 6 is coming 1.86. Then 17.34% of 6 is coming 0.97. Then this is 1.6, this is 0.09, and altogether it is basically 6. Okay, so what I am doing, I am calculating what could be the expected count that of means, suppose based on their fitness value. So expected count of the first solution is 1.61. So how I am getting it? So this 1.61 I am getting it that 26.88% of 6 basically. So this is 1.61. Okay, so now this is the expected count, but you cannot select your 1.5 solution or 1.61 solution. So what you have to do, the solution either it will be selected or it will not be selected. So therefore its value has to be an integer. So what I'm doing, I'm just rounding up. So 1.67 I am putting it 2, then this is 0, then this is 1, then this is 1, then this is 1, and this is 1, and all together you are getting total 6 solution together. Okay, so here what is happening, that solution 1 is the base solution, so it is having 2 copies. Okay, then the solution 2 is the worst solution, it is having 0 copies, and other solution will be either 1 copies or 2 copies. So in this case you are getting 1 1 1. Okay, so 1 1 1 1, so total 4 solution plus 2, so you are getting 6 solution. So now what you are getting from here, the solution 1, that is chromosome 1 will have 2 copies, then chromosome 2 will have 0 copies, 3 4 5 will have 3 4 5 6 will have 1 copies, and total you are getting 6 copies, and they will be selected for the next generation. Okay, so I think this is not that difficult, so I can write a simple code in any language I can write. Okay, so to implement this particular algorithm, so I am selecting based on the roulette wheel, or basically based on the proportion of the your that solution occupying the roulette wheel. Okay, so I hope this is clear to you. So now what is the disadvantage of this proportionate selection? Okay, so if you look at, now what is happening, we are selecting the parents based on the fitness value. Now question is that, suppose there is a particular solution and whose fitness value is very high compared to the fitness value of the other solution. Suppose you are getting one solution and that fitness value is very high. So in this case I have shown an example. The solution 1, the fitness value is 80. Okay, and compared to other solution that second one is 6, then 20, 25, 10 and 18, the solution 1 is basically, the fitness value of solution 1 is very high. Okay, then what will happen, because the fitness is very high, so he will occupy more space in the roulette wheel. So in this case he has occupied almost 50%. Okay, so 50% of the roulette wheel. So therefore, but other solution is occupying lesser okay percentage, that means this is 4%, 13, 16, 6, 11, and altogether it is 100%. Now now what will happen, that because it is occupying more space on the roulette wheel, so probability of your selection of this particular solution is very high. Okay, so probability of selection is very high. Okay, and so therefore what will happen, that particular solution will dominate the population. So in this case what is happening, the expected count is 3. Okay, Then so now what will happen, so we are having we'll have three copies of the this particular solution because of this fitness value is very high. Now if it is, suppose if it is one if it is not 80, suppose it is 150, then it will have more copies, maybe your 4 copies or 5 copies of this particular solution. Then what will happen in the population, so this will have 4 copies and there will be another 1 copy, so that means the population will be saturated with the base solution. Okay, so therefore sometime if you are getting a very high suppose fitness in a particular solution, then in the proportion selection that particular solution will dominate the population. So out of 6 you are having that a particular solution will have 4 copies or 3 copies, and that is not a, as I say, this is not a healthy situation. It is just like you are increasing the selection pressure. Okay, so once you are increasing the pressure, so what is happening, that will dominate the population. Okay, so that is not a healthy situation. We want diversity in the population. Okay, so therefore we want to avoid that one. So we don't want means one that a particular solution is dominating that population. Then what will happen after some time, so you will not be able to create a new solution. That I think you will understand once we are discussing the crossover means suppose that crossover operator. Okay, so you will not get new solution. The crossover will not be able to create new solution, only mutation will create. That means your search process will be dominated by only mutation. Okay, crossover will not have any effect if your population is saturated by a particular solution. So that is, as I said, that is not a healthy situation and we should avoid that one. Okay, so therefore what to do basically, how to avoid that. Suppose if you want to use proportionate selection and you want to avoid that the particular solution should not dominate the population. Okay, so what you will do basically, that I can use the rank selection. Okay, so I can use the rank. Let us see what is rank selection. So in rank selection what I'm doing basically, so I will sort the data. So our idea is to avoid that selection of a particular solution only, because if in the case of that if you have a very high value in a particular high fitness value of a particular solution, so I would like to avoid that one. Okay, so what to do basically, how to avoid? So as I said, I can use rank selection. So in rank selection I am taking the same example problem. Okay, so this is basically that the fitness value of, as I said, that first solution is 80, then second is 6. Okay, like that. Then I am just arranging it in your uh, descending order. Okay, the highest value at the top. Okay, then the second highest, something like that. So I am just in a decreasing order, I'm arranging the population. Okay, so I can do the sorting. This is not very difficult. I can do the sorting and I can arrange in a descending order. The highest value will be at the top and the lowest value will be at the bottom. Okay, so this is basically I'm doing the sorting according to fitness. Okay, next what I'm doing, I am assigning a rank to them. Okay, so you are assigning a rank. So the base solution is getting the highest rank. Okay, what is highest rank? It is the number of your solution in the population, number of your. So here we have 6 solution, the rank is 6. Okay, then second one rank is 5, then 4, then 3, then 2, and then 1. So I am putting a rank like this, that the highest fitness value solution will get rank highest rank, that is the 6, and then you are decreasing the rank. Okay, and the lowest value. Okay, so worst solution will get a rank 1. Okay, so in now what I'm doing now, I am just use this rank to calculate the percentage of roulette wheel. Okay, so now what is happening, it is now 20, it is occupying 29%. If you look at the first solution, that is the base solution, in the earlier case if you take the fitness value, so it has occupied 50% of the roulette wheel, but now it is 29%, and this is 24, then 19, 14, 10, and 5. Okay, so this is the percentage of roulette wheel occupied by different solution. So let us draw the roulette wheel now. So this is the roulette wheel. Okay, so this is your 29%, then 24%, this is 19, then this is 14, this is 10, and this is 5%. Okay, now you play the roulette wheel. Either you play the roulette wheel for 6 times, or you can use the proportionate selection. So if you are using proportionate selection, now what is the expected count? Expected count is, that is 1.71, and this is 1.429, and this is 1.143, this is 0.857, and this is 0.571, and this is 0.286. Okay, and this is the expected count. And what is actual count? As I said, that I cannot use 1.5 of the population, so it has to be your integer value. So I have rounded up, so that means the first solution will have 2 copies, second solution will have 1 1 1 1 basically. So total you are selecting your 6 solution. I hope this is clear. So this is basically the rank selection. So just to avoid the saturation of a particular solution. Okay, so I don't want that a particular solution is dominating the entire population. I want the diversity. That means the inferior solution also I want to keep in the solution in the pool to increase to have the diversity. Otherwise you will not be, your search process will be means suppose you will not be able to create new solution. Okay, so if it is one particular solution is dominating the population. Okay, so this is basically the rank selection. So there are some other your selection method also, okay, algorithm also, so I'm not discussing here. So you can use tournament selection, you can use proportionate selection, you can use roulette wheel selection, you can use rank selection, and then I think we can write a simple code and that to implement this selection operator. So the concept is not very difficult, and only thing is that so you have to implement using say writing some code. Okay, so that you are doing. So I hope this is clear to you. Now let us discuss the crossover operator. Okay, so now selection operator is over. Okay, so we can use one of them to create multiple copies of the better individual. And what we are doing, we are eliminating the inferior solution. The worst solution will certainly, it will not be there, and some of the inferior solution will also be eliminated. Okay, now let us see crossover. What is crossover? So crossover, the main purpose of crossover is to create new solution, because selection operator is not giving you new solution. What it is giving? It is giving multiple copies of the better solution, and you means inferior solution or worse solution you are eliminating from the pool, but you are not getting a new solution. But if you want to search, that means you have to create new solution. Okay, so how to create new solution? The crossover is creating new solution, and as well as mutation also, so that I will discuss. Okay, so crossover operator is used to create new solution from the existing solutions available in the mating pool after applying selection operator. So after applying selection operator, whatever solution you are getting, so that is we call mating pool, and from that mating pool, so I would like to create some new solution using crossover. Okay, this operator exchanges the gene information between the solution in the mating pool. So what crossover is doing, it is exchanging the gene information between the solutions. Okay, so that is even if in the biological crossover also it is happening. So that is basically that from both the parents gene informations are happening through crossover, and that's why the cell has the characteristics of both the parents. Okay, so here also the gene information, exchange of gene information is you're happening yeah, so in this particular stage. So this is the biological crossover. Okay, so and you know that the crossover is basically a chromosome is composed of gene, and gene is basically carrying the characteristics of that particular solution or portion basically. Okay, now like the biological crossover, so our crossover is much more simpler than or our chromosome is much more simpler than the biological chromosome. So here what is happening, so but I want to have a structure like a gene, so altogether I am calling it is this one as a chromosome. Okay, so this is a chromosome, and this chromosome is composed of gene basically. Okay, so this is gene. Okay, so these are all genes, and these genes are carrying the characteristics of that particular individual. Similarly here also this gene is carrying the characteristics of that particular solution. Okay, so this is basically our simple mathematical crossover, and maybe what I can do basically, suppose if I convert our your solution to a binary value basically, then what will happen, so I will have either 0 and 1 information, and in this case what will happen, that these are the gene, the probable value of the gene is either 0 or 1 basically, and now this is basically carrying the characteristics of this particular solution. Okay, so you just see that if you are changing this value, okay, so whatever the corresponding sign in the in the decimal value will be less. Suppose if you are changing, suppose this particular chromosome is changed from 0 to 1, but if you are changing the chromosome here sorry, if you are changing the gene on the other hand side, so in that case what will happen, that solution will be a different solution. Okay, so I will also explain that one, so when I will take a numerical value. So encoding of solution is therefore necessary so that our solution looks like a chromosome. So what you have to do, you have to do the encoding, and so that the solutions look like a chromosome. So in this case we are using binary bit. Okay, and therefore this genetic algorithm is also known as binary coded genetic algorithm. So it's a binary coded genetic algorithm, and this is actually initially it has been developed something like that because I want to have his similarity between biological process, whatever biological chromosome and this thing, and with that, so what people have used the binary your bit. Okay, and that's why this algorithm is also known as binary coded genetic algorithm. So we'll also discuss real coded genetic algorithm, where directly we are using the real number, not the binary value, but in this case we are using binary your code, binary coded or binary values. Okay, so now what is encoding? The process of representing a solution in the form of a string that conveys the necessary information is called encoding. Okay, so now what I'm doing, suppose this is the population, so we have 1 2 3 4 5 6 7 solution here, and basically I'm getting 7 chromosomes. So here this is the first chromosome, so this is the first chromosome, this is second chromosome, this is third, this is fourth, something like that. So it is basically I'm getting total 7 chromosomes. That means in a population I have 7 solution, or I can say that 7 chromosome I have. Okay, and now basically then each solution, okay, so this is basically in the chromosome, suppose there are several variables, suppose in this case this is x1 value, this is x2, then this is x3, x4, something like that, and this is xn. So we have actually xn values. Okay, and then the each variable, so we have converted to binary bit. Okay, similarly what I can do basically, so I can use the binary bit for each of the variable, or otherwise I can also use a real value. Okay, so this can be a binary value or this can be a real value, or sometime what we do basically, that part of the chromosome is considered the binary and part of is a real value. Okay, so that also I can use, and in that case this is known as hybrid your chromosome. Okay, so what we are getting here, we are getting binary chromosome, we are getting real chromosome, and we are getting hybrid chromosome. Okay, so I will also discuss how you can do this encoding. Just as in a chromosome, each gene control a particular characteristics of the individual, similarly each bit of the string represent a characteristic of the solution. Okay, so what is happening, this each bit is also you're representing the characteristics of the solution. Okay, so if I change any particular bit, if I change it from 0 to 1 or 1 to 2, then solution will change. So it is representing the character, and what is happening, the position is also important. Okay, so if something is selected, as I said, on the right hand side, then whatever corresponding change in the real value will be very less, but if something is changed in the left hand side, then corresponding change in the your real value will be very high. So therefore this is also your the position is also matter, not only the value but position is also matter. Okay, so we'll discuss this thing in some in more details. Okay, so when we'll solve an means of when we'll do an hand calculation of an simple problem, so there I will explain the things actually again. But idea is that the real value you convert to binary value just to look like a chromosome, and so that you can apply the concept of crossover and mutation you can do. Okay, so right now we will discuss the binary coded your GA, that means binary chromosome we will consider, and later on we will also discuss about real coded. We will also discuss what is the disadvantage of binary string, and then what basically how you can overcome those things by using your real values. Okay, so that's why we'll discuss, but right now we'll discuss the binary coded GA. Okay, binary string. Okay, so how to do the encoding? Most common method of encoding is binary coded. Okay, so chromosomes are strings of 1 and 0, and each position in the chromosome represent a particular characteristics of the problem. So here I have shown a string, so this is a chromosome, or you can say string. So it has two variable, the variable 1 and variable 2. So I am taking 1 2 3 4 5 6. Okay, so 6 bit I am taking to represent variable 1, and another 6 bit I am taking 1 2 3 4 5 6, another 6 bit I am taking to represent the variable 2. So now if I say that the first string is 1 1 0 1 0 0, so the corresponding decoded value is 52. Similarly, this is basically, suppose this is 0 1 1 0 1 0, the corresponding decoded value is 26. Okay, so now if I change any bit, okay, so if this is changed to 1, then this value will change. But as I said, that if this value is changed, then what will happen, this value will slightly change, so 1 will mean, so these are lesser significant values. So if you are changing this value, then corresponding change in the solution will be very less, so you are getting a solution near to that. But if something is changed here or here, then what will happen, the corresponding change will be very high, the decoded value, change in the decoded value is very high. Okay, so and then we can do a mapping between decimal and binary values. So this mapping is use something like that, the xi is equal to x minimum plus x max minus x minimum to the power l minus 1 to the power l minus 1 into decoded value. So I can use this mapping. Okay, so what will happen that if I am using all 000, okay, so in that case I should get the lower bound, that is x minimum, and if I using all 1111, then I should get the x maximum, and for other values, so I will get the between x max and x minimum. Okay, so I can use this mapping here, so mapping here to map the binary string to the decimal value. Okay, so let us see this example problem, the same example problem I have considered here. So the minimization of that your cost of a can. So I would like to design this can, subject to that volume should be greater than 300, and the D and H value should be between minimum value and maximum value. Okay, so now defining a string like this. Okay, so I have defined a string, so 6 value I am using for D, another 6 value I have used for H. So in that case, suppose 0 1 0 0 0, so this is the D string, and this is for H, the variable 1 and variable 2. Okay, and the corresponding value is 8 and 10. Okay, so just I'm not using the decoded way. I mean, suppose the mapping I have not used, but the corresponding value of your decoded value of D is 8, and for H is 10 centimeter. Okay, so what I'm getting, so this is the decoded value, and so this is the chromosome, and you can use the you can calculate the cost of this one. So this is representing this particular solution, that is D equal to D equal to 8 and H equal to 20. I hope this is clear. So we have encoded the solution to a chromosome basically. So we have considered the solution in terms of chromosome, and from this chromosome I can actually find out what is the value of D. So as I said, the first 6, 1 2 3 4 5 6, so first 6 is representing D and second 6 is representing H. Okay, so now what is crossover? So in order to apply crossover, so what you have to do, you have to convert your solution to a binary bit. Okay, so that you are doing using that mapping. Okay, so you have converted that solution to binary bit, then you apply crossover. So biological crossover is very complicated, so we are not considering but in our case we are considering a very simple crossover. Okay, so let us see that one. The most popular crossover selects two solution string randomly from the mating pool, and some portion of the string is exchanged between the strings. Okay, so what we are doing, we are selecting two solutions. Okay, so from the mating pool. So I think if you take the example problem we have discussed, so we have 6 solution or 6 solution in the mating pool. So that is after implementation of selection operator, and from that 6, so I am considering, I am just taking 2 solution, and this is the 2 solution, and then then a crossover site is selected. So a crossover site is selected, so this is solution 1, this is solution 2, and then a crossover site is selected, and after that you just swap the information. So what you are getting, so you are getting something like that. So this is basically going there, and this portion is coming here. So therefore whatever new solution you are getting, the child 1 and child 2, and this is parent 1 and parent 2, so it has the information from the parent 1 and parent 2, that solution 1 and solution 2. So this portion of the solution 1 and this portion of the solution 2, so you are getting a new side. Okay, similarly from this solution of the solution, this portion of the solution 2 and this portion of the solution 1, you are getting a new string, and that is basically a your new style you will get. So what I'm doing here, using crossover operator, so crossover, so I am creating a new solution. And what is new solution? That some portion of the solution 1 and some portion of the solution 2 we are adding, and means we are taking, and then we are getting a new solution. Similarly for the second solution, that some portion of the second solution plus another portion of the first solution we are taking, and we are getting a new solution. Okay, so what is happening here, that you are using two solution, two parents, basically that from the parents, so you are getting two your child or two children you are getting here. So and basically, so two your from two solution you are getting another two new solution. Okay, so now question is that in the population, whether you will allow each of the solutions, suppose you have 6 solutions in the population, whether you will allow all of them to go for crossover or to go for crossover or not. So that is basically controlled by a probability, and we call it your probability of crossover. Okay, so this is called, we call probability of crossover, and it is giving a freedom to a particular solution whether he will go for crossover or not, basically. So without going for crossover also, he can actually go to the next generation. So therefore this is controlled by a probability. Okay, and this probability is known as crossover probability. So generally we keep very high crossover probability, maybe your 0.6 to yeah 0.9 or 0.95. Okay, so the 0.95. So we generally keep very high crossover probability. That means we want that all means a almost 60% to 80% of the solution they will go for crossover, and they will create new solution. Okay, so maybe one or two solution, or we can allow them to go to the next generation without participating in the crossover. Okay, so that okay, so this is basically we can. So here also what I can do, I think concept is again very simple. So what you are doing, you are decoding. Okay, you are converting that solution to a binary bit, and after that you are applying crossover. So you can write some you cannot implement it manually, so what you have to do, you have to write some code to implement that one. So crossover I can actually write a simple code to implement this crossover. And here what we are doing, we are taking a single side, that means one side we have taken, and then corresponding your values we have your exchange. Okay, so this is basically one example of crossover. So this is again for the can problem. So this is the same thing I am explaining. This is parent 1 and this is parent 2, and then after crossover, so you are getting child 1 and child 2. So one portion of the parent 1 and second portion of the parent 2, so you are getting child 1, and then first portion of the parent 1 and parent 2, and second portion of parent 2, so you are getting child 2. Okay, now let us take this can problem. So one solution is 8 and 10, so I can convert this 8 and 10 to this binary bit. So first 6, 1 2 3 4 5 6, 1 2 3 4 5, I think 5, and then 1 2 3 4 5. So this first 5 is basically the first variable 1 and variable 2, and similarly second one is 14 6. So we are doing the crossover side. So after third, so this crossover side again is selected randomly. Now question is that how to select randomly. So you generate a random number between 1 to n minus 1. Okay, so or you can say, suppose there are total your n bit. Okay, n bit number of bits. So in this case, how many bit we have? 10. 1 2 3 4 5 6 7 8 9 10. So n equal to 10 basically. So what you are doing, you are generating a random number between 1 to n minus 1. Okay, so you are generating a random number. So now this is done randomly. So suppose in this case it is coming 3, that means after 3 you are putting the crossover side. And now you exchange this, what will happen? This portion will go to the first solution, and this portion will come back to the second solution. So now this is basically, so I am getting this solution. So this is 0 1 0, and then basically 1 0 0 0 1 1 0. Okay, so this is the child 1 I am getting, and this is the child 2 I am getting, and this solution is 10 6 now, and this is 12 10 now. So I'm getting a new solution by two new solution by this crossover operator. So sometime what happens, so we are also using two sides. So in this case we are using single side, but sometimes we are using, this is two side I am using, and in that case, so this portion is exchange. Okay, so this portion is exchange, and you may have two side, three side, something like that, and you may have different your crossover means suppose operator, you mean suppose you may use different crossover operator. So here I have shown you single site and your multi-site crossover, that is more than one, and basically you can apply one of them. Okay, so in this case what I'm getting, so earlier solution, this solution is 23 and this solution is 37, and after implementation of cross operator I am getting another solution, one is 22 and one is 39. Okay, now let us look at this operator. What is happening? The earlier solution is 23, now in new solution you are getting 22, and earlier solution is 37 and new solution you are getting 39. What does it mean? Basically what you have observed, that we have observed that whatever new solution is created, it is just near to the parent solution. Okay, so it was 23, now you are getting 22, it was 37, you are getting 39, but you are not getting a solution. Earlier it was 23, suddenly you are not getting 15, or it is 37, you are not getting something like that. Okay, so something like 10 or something like 50 you are not getting. So what you are getting, your children are near to parents. Okay, so this is one of the characteristics of crossover, that what you are doing basically, so you are trying to create a solution near the parents. So if you look at it, what is that? That means you are creating, suppose you are here somewhere, you are getting a, this is your parent 1 and this is your parent 2. So what is happening, you are creating a solution near to the parent. So this is new solution and this is also a new solution. That means the crossover is doing, what crossover is doing? Crossover is doing the local search. That means it is just searching near to the existing solution. Okay, near the parent solution. Okay, so this is parent 1 and this is parent 2, and you are getting, this is child 1 and child 2. So you are not getting a solution somewhere here. So you are not getting solution somewhere here. So what you are getting, you are getting a solution near to the parent. So therefore the crossover is doing the local search. That means it is locally searching near the parents. Okay, so I think this is one of the characteristics, and basically we are doing the local search. That means if there is any improvement locally, so that we are doing. So this what is this parents? Parents are all the solutions. Okay, and then we are trying to see, is there any better solution in the nearby of this solution? So we are doing the local search using the crossover operator. I hope this is clear to you. Now next is mutation. So what is mutation? So mutation is occasional introduction of new features in the solution string of the population pool to maintain diversity in the population. So what is happening? This is an occasional introduction of new features. That means you are somehow, the gene information has been changed. That is basically, we call it mutation. Okay, so though crossover has the main responsibility to search for optimal solution, mutation is also used for this purpose. Okay, the purpose is what is the objective is same. That means you want to create a new solution. The crossover has created a new solution. Okay, so mutation also, the objective is same, that I would like to create a new solution using mutation. Okay, but there are some difference. I will explain. So this is basically how we are implementing mutation. That basically, suppose this is before mutation, so this is before mutation. So you have this solution, and due to mutation this gene information is changing. So in this case, the binary coded GA, what I will do, I will change this particular bit. If it is 0, I will convert it to 1, and if it is 1, I will convert it to 0. That is the only possibility we have actually. So we can convert 0 to 1 or 1 to 0. Okay, and this is your mutation. Now let us see this example problem. So mutation operator sends a 1 to 0 or vice versa. So we with a mutation probability of PM. Okay, so with a mutation probability of PM I am using. Now this I will discuss what should be the value of PM. The mutation probability should be kept very low. So I don't want to have a very high value of mutation probability. Okay, I will explain that one. And it should be very low. Low means maybe your 0.01 your suppose 1% or 2%, something like that. And generally we are taking a thumb rule is that PM should be 1 by L. Okay, L is the string length. So if your string length is 10, then the probability is 1 by 10. So what does it mean? What it means that on an average, so what will happen, one bit will be mutated out of your 10 bit in a particular cell. Okay, so it is 1 by L you are taking. Now this is an example problem. So here this is before mutation it was 1, and after mutation it is 0. So and how to implement that one? So with a mutation probability of PM. So what you will do basically, so suppose your cursor is here and you are creating a random number between 0 and 1. If the random number is less than mutation probability, you will mutate it, otherwise you will not mutate it. Okay, then you will go to the next bit. You generate a random number. If the random number is less than mutation probability, you will mutate it, otherwise you will not. So that way you are going from left bit to right bit. Okay, so the probability is, if you are using 1 by L, that basically on an average, that means suppose if you are doing your large number of means suppose iteration, then what will happen, that one of in a particular iteration, that one bit will be mutated out of the L bit. Okay, so this is the idea of using 1 by L, the probability. Okay, so now if I take the same example can problem, so this is before mutation I am having, and this is 22, and this is after mutation. So I am changing this to your 0. So this is basically, so I suppose with some mutation probability that third or fourth bit is mutated. So in that case, if it is 1, then it will become 0, and I am getting 16. Okay, so what does it mean basically? So from 22 I'm getting 16, but it may happen something like that, that if suppose this particular bit is changed, okay, so this bit is become 1, then what will happen, from 22 it may be 37 or something like that. Okay, so therefore the mutation is, it may create a solution, because if suppose this bit is changed, then what will happen, it will create a solution near the existing solution. But if the left hand side bits are changed, then there may be some you may create a solution at different locations. Suppose you are here, if the right bit is changing, so you are getting a new solution. But if somehow left bits are changing, so you may get solution here or here. That means what we are doing here with the mutation, we are trying to explore the unexplored region basically. So you are here with crossover, you are searching locally, but with mutation you are trying to search globally. Is there any other region, unexplored region, where there might be a better optimal solution? Okay, so therefore we need mutation. Only crossover will not work. I can also give an example why it is not working, crossover. Mutation is also required. Okay, so with mutation, because mutation can explore the unexplored region. Okay, so using your if somehow if it is changing the left side, okay, most significant bit, then you are exploring the other region too. So therefore the mutation is also your required. So it's a combination of crossover and mutation. So we have discussed all these all these operators. So we have discussed crossover operator, we have discussed mutation operator, and we have discussed uh, the selection operator. So if we apply these three operator, then what will happen? It is expected that every iteration you should get some improved solution. Now question is that there may be some question what is happening, because you just see when you are applying crossover and mutation, it's not that always you are creating better individual. Okay, sometimes what may happen, crossover may create an inferior solution than parents. Okay, so the children whatever you are creating, that may be inferior their parents. Similarly, after mutation, what solution you are getting, that may be inferior than the existing solution. So therefore, but if it is happening, you need not worry, because if there it may happen sometime, but what will happen that when it will go through the selection operator next time, if mutation and crossover is creating some inferior solution, that inferior solution will be eliminated through selection operator in the next iteration. So therefore you need not worry about that one if they are creating, but if they are creating good solution, that will be preserved. Okay, so let us stop here, stop the discussion here. Tomorrow again I will continue this discussion. I will solve a simple problem using I will just do the hand calculation of a simple problem. Okay, just to explain all this process, how to create initial solution, then how to do selection, how to do crossover, and how to do mutation. Okay, so let us stop here. Tomorrow again we'll discuss. If you have any question, you can ask me at the end of the class. Thank you.